Okay, so for part 3 of our SAT math series, we're going to look at problem solving and data. So this is where we'll look at statistics and how they relate to each other, and we will have to do some inferring here and decide upon things ourselves. So first, there's 17 questions on this topic on the SAT. And these questions assess our ability to use our math understanding to solve problems set in the real world. So we might have to create a representation of a problem, consider the units involved, pay attention to the meaning of quantities, and know and use different properties of mathematical operations. Okay, so the questions involve quantitative reasoning about ratios, rates, and proportions, and may require understanding and applying of unit rates. Some questions present information about the relationship between two variables in a graph, a scatter plot, a table, or another form, and ask you to analyze and draw conclusions about the given information. Okay, so we also might have to analyze data presented in dot plots, histograms, box plots, basically anything that is a visual representation of data. Okay, so the first thing to talk about is ratio, proportion, units, and percentages. Okay, so a topic that that you guys have done throughout your math education in school. So a ratio is just a comparison between two or more quantities, and represent how many of each are accounted for. So the ratio in this picture, the ratio of blue to yellow squares is 3:1. Okay, which means there's 3 blue for every 1 yellow square. Okay, so we can reduce and increase ratios just as fractions. So 3:1 can also go to 6:2, which would just mean instead of 3 blue for every 1 yellow, now there's 6 blue for every 2 yellow. Okay, so the ratios staying the same, are just our proportions are going up. Okay, we can also represent ratios as fractions of the total. So if we were looking at the amount of squares here and trying to decide what the percentage or what fraction the blue squares would be, okay, we would just end up with the amount of blue divided by the total amount of squares. Okay, so in this case, it'd be 3/4 of these squares, okay, or 75% would be blue. Okay, so just a quick review of what ratios are. And let's look at some examples. So on Thursday, 240 adults attended a show. The ratio of adults to children was 5:1. How many children attended the show? Okay. So when we're looking at a total here, we have a total of 240 guests. Okay, and I want to know how many were children. Okay, so I either need to know what percentage of people were children, or represent that as a fraction. Okay, so here, if I were to get a fraction of children, I'd want the number of children, say number of children, okay, divided by the total number of people. Okay, and we would have 1, so 1 child for every 6 people. Okay, so all we do now is just multiply this by 1/6. Which would just give us 240/6, which is 40. Okay. So something to note here is that if I were to look at now the ratio of adults to children, okay, I would have 200 adults and 40 children. Okay, and if I reduce this, okay, I could divide each of these things out by 40, and I would just be left with 5:1, which is my original ratio that they gave me. Okay, so just a quick check that lets me know that my answer is right. Okay, so on an architect's drawing of a floor plan for a house, 1 inch represents 3 feet. Okay, if a room is represented on the floor plan by a rectangle that has sides of lengths 3.5 inches at 5 inches, what is the actual floor area of the room in square feet? Okay, so initially I know that we have 1 inch for every 3 feet. Okay, so then when I look at the length and width of this room, okay, we'll say my length, I'm still going to use the same ratio. Okay, but now I want to know what is the length if it's 5 inches on the sheet. Okay, so what I had to do here was I had to multiply 1 times 5. So I will obviously just do the same with this, with the 3, and I'm left with 15 feet. Okay, so this was 1 inch represents 3 feet, so that would mean that 5 inches represents 15 feet. Okay, so there's my length of the room, my width of the room. Okay, I'm going to use that same ratio. Now I'm going to multiply them all by 3.5, because it's 3.5 inches. Okay, and 3 times 3.5 would leave me with 11.5. Sorry, that's a lie. I lied to you. 10.5. Okay, and then they want to know the floor area. Okay, so now I can take my length and width and just multiply them. So area equals length times width. In this case, that equals 15 times 10.5. Which gives me 157.5. Okay? So they gave me my original ratio, and then from there, I had to adapt that ratio to get my length and width. Okay, so rates. Okay, we've seen this term a lot when referring to slopes. Okay, but we use rates to see how much of one thing is happening per one unit. Okay, for example, 120 kilometers an hour is a rate, and it means that I'm traveling 120 kilometers for every 1 hour. Okay, another one would be a heart rate. Say it was 61 beats per minute. Okay, I'm measuring 61 beats every minute for every 1 minute. Okay. So a coastal geologist estimates that a certain country's beaches are eroding at a rate of 1.5 feet per year. According to the geologist's estimate, how long will it take in years for the country's beaches to erode by 21 feet? Okay, so again, this is just a ratio. I'm saying 1.5 feet for every year. Okay. In this case, I can write it like this. Okay, and I want that to equal time. I don't know what t is in this case. I don't know how many years it's going to take. Okay, so I can solve this just like any old other function like this. I just need to solve for t. Okay, so in this case, I can cross multiply. Okay, I'd be left with 1.5 t equals 21. Okay, I'll divide both sides by 1.5. I'll be left with t equals 21 divided by 1.5, which would give me 14. Okay, so at a rate of 1.5 feet per year, it would take 14 years for this beach to erode 21 feet. Okay, so scientists estimate that the Pacific Plate, one of Earth's tectonic plates, has moved about 1,060 kilometers in the past 10.3 million years. What was the average speed of the Pacific Plate during that time period in centimeters per year? Okay, now underline centimeters per year, okay, because my original measurement is in kilometers. Okay, so it's kind of giving you a hint that we need to change our units. Okay, but this is 1,060 kilometers, and it took 10,300,000 years. Okay, so all I need to do in this question is, first I have to take these kilometers and put them into centimeters. Okay, so to do that, I know that there's 1,000 meters in a kilometer, and I know that there's 100 centimeters in a meter. So I'll take 1,060, multiply it by 1,000 to get it to meters, and then multiply by 100 to get it into centimeters. Okay, so when I do that math, I'm left with 106 million centimeters, and I'm still dividing by that same 10,300,000. Okay, and then I'm just left with 10.3. And if I look here, okay, my units, I have centimeters on the top, years on the bottom, so I could say that this is centimeters per year. Okay, so my answer in this case is B. Okay, so percentages. Okay, going on the same topic that we've been talking about. Okay, another area where we're pretty familiar with what percentages are, but what they are is it's just another ratio or proportion. And in this case, instead of a rate being per year, a percentage is per 100. Okay, so for instance, 20% would mean 20 out of 100. Okay, so percent increases or decreases, we can calculate those by finding the difference between two quantities, then dividing the difference by the original quantity. Okay, so percentages are in the amount in each 100, so 3 out of 4. 3 out of 4 is also 75 out of 100, which gives us 75%. Okay. Now, one thing to note about percentages is when we're dealing with them in equations, okay, we always want to turn them into a decimal. Okay, so to do that, 75% is just equal to 0.75. Okay, we can take our percent and divide it by 100 to give us our decimal. Okay, so this question here, 72% of a number is 14.4. What is the number? Okay, so some keywords here. Whenever we see the word of, okay, we will talk about multiplication. Okay, and whenever we see the word is, sorry, there should actually be is right here. Okay, is always means equal. Okay, so this line right here, this is 72%. First I turned it into a decimal, and then I multiplied it by n. In this case, n is just a variable, and is means equals 14.4. Okay, so I would divide both these by 0.72. So 14.4 divided by 0.72 is just 20. Okay, so a furniture store buys its furniture from a wholesaler For a particular table, the store usually charges its cost from the wholesaler plus 75%. But during a sale, the store charged the cost from the wholesaler plus 15%. So if the sale price of the table was $2.99, what is the usual price for the table? Okay, so one major thing to notice here. Okay, whenever we're dealing with cost, okay, we will take, when it says a cost plus 75%, okay, really what we're doing is we're going to multiply that by 1.75. Okay, in this case we would multiply by 1.15. Okay, the 1 here just represents the full cost of the original table. Okay, and then we're going to add another 15% to it. Okay, so an example of this that we're all familiar with is when we're calculating the tax on something. Okay, if I buy a shirt, say, for $10, if I buy a shirt for $10 at 13%, okay, to get the total cost of the shirt, I want to multiply by 1.13. Okay, which would give $11.30. Okay, if I were to multiply by just 0.13, it would give me 1.3, which is like saying the tax is worth $1.30. Okay, but the total cost would be $11.30. Okay, so for this question, the sale price of the table was $2.99. Okay, and that was happening at the wholesaler cost plus 15%. Okay, so I know that 1.15, okay, times P, we'll just say P is the price. We know that this equals $2.99. Okay, so we just solve for P, divide by 1.15. So the price from the wholesaler is $2.99 divided by 1.15, which is $2.60. Okay, I want to know the usual price, and they usually charge 75%. So now I'll say $2.60 times 1.75 equals, I'll call it U, just usual price. Okay, when I do this, U equals 4.55. Okay. So this pretty basic question here, if 10 is 2% of Z, what is 50% of Z? Okay, so first we need to solve for Z here. We have enough information to do that. And if I were to put this into an equation, okay, 10, then I see the word is means equals. 2%, I want to convert that into a decimal, times Z. So again, divide by 0.02. Z equals 500 in this case. Okay, and then I just got to do one more step. They want to know what 50% of Z is. Okay, so this is 0.5 of 500. Okay, it just equals 250. Okay, so a lot of these problems will be maybe two or three step problems. Okay, both of these have been in this case, two-step, where first we have to get an original price or an original amount, and then adapt it for what they're asking us. Okay? So, interpreting relationships presented in scatterplots, graphs, tables, and equations. Okay, so terms to know here will be maximum and minimum of a function and what they mean, and then a correlation between two values. Okay, so the first, just looking at this picture real quick. Okay, the max and minimum, obviously maximum is the highest that we can get. Okay, minimum is the lowest we can get. Okay, so the term local maximum just means in this region. This is the highest point in this region. Okay, global maximum would be the absolute biggest one on the graph. So this is the highest point in this function. So this would be the global maximum. And we'll talk about correlation in a second. Okay, so first, max and minimum. Okay, so the complete graph of the function f is shown in the xy plane above. For what value of x is the value of f at x at its minimum? Okay, so first, the minimum is again the lowest point, which is occurring right here. Okay, we just want to know what value of x, so where that's happening. So this is -1, -2, -3. So x equals -3. That's my answer here. Okay, but take this one step further. My minimum value is just my y. Okay, so this has a minimum of -2, and it's occurring at -3. Okay, so does y equals -2 and x minus 4 squared plus 3 have a maximum or a minimum? Okay, so we have to have a little bit of knowledge and go back to what we know about quadratics. Okay, this is in vertex form. Okay, my vertex is at 4 and +3, so 1, 2, 3, 4, somewhere here. Here's my vertex. Okay, but what I know about this vertex is that because my a value is negative, I know my parabola is opening down. Okay, so I know that this becomes a maximum because this will now be the absolute highest point of this function. Okay, so taking this idea and another step further, so what is the value of the minimum? Okay, this is asking for basically what's the y coordinate of my minimum. Okay, so if I were to graph this one, my vertex would be at -4, -5. Okay, so somewhere down here. Okay, my a here, I can decide is 1. So I'm opening up. Okay, so the value of the minimum is just the y coordinate of the vertex. So the value of the minimum is -5. So my min equals -5. Okay, so moving on, maximum and minimums. We just have to know what they are. We won't have to do a whole lot with them, but this question here is a good representation of the type of questions we'll ask about max and min. Okay, so correlations and lines of best fit. Okay, so this correlations is how strong a relationship is between two variables. Okay, so the more related two variables are, the stronger the correlation. Okay, the less related, the weaker their correlation. Okay, so positive correlation just means we have a positive slope in this case, so we're going up to the right. Okay, and it just means that as one variable increases, okay, the other also increases. Okay, so an example of two variables with a positive correlation would be, say, the hours spent studying, okay, and this would be your test mark. Okay, so if I studied for, say, this was 8 hours, okay, I could expect to get a pretty high test mark. Okay, if I didn't study very much, I'll probably have a lower mark. Okay, so negative correlation. So now as I increase in the x direction, I'm actually decreasing in the y direction. Okay, so an example of things with a negative correlation might be, we'll stick with the test mark. So this is my test mark, and my y axis. My x-axis might be hours spent watching TV. Okay, so if I watch a whole bunch of TV, okay, I'll probably end up with a lower mark. Okay, and then if they have no correlation, it means they're scattered all around the graph. Okay, that means there's no connection between the two variables. So maybe, say, age and hair length. Okay? Okay, so here's a table of values. Okay, and we're going to look at attendance percentage compared to the overall grade. Okay, so if we look, now if we want to make a line of best fit, okay, what a line of best fit does is it takes data like this, and it gives us a representation or an approximation of the relationship between the two data. Okay, so when we're creating a line of best fit, okay, we want all of these points to be accounted for, and we want to have roughly the same amount on the top of the line and on the bottom of the line. Okay, so we want this to basically run right through the middle if we can. Okay, now every line of best fit will be different. Okay, but as long as they are close, okay, if we were to draw something like this, obviously that would be wrong. Okay, because it's not running, it's not really accounting for all of the points. Okay, but if I were to run it roughly right through the middle here, okay, all of these points are accounted for. They're all roughly the same distance away from this line. Okay, and any variation of this line, as long as it's close, okay, will be okay. Okay, to get the equation of a line of best fit, okay, first you can check, does it go through 2 points? In this case, mine does. It goes through this point and this point. So I can use those 2 points to get the equation of the line. Okay, so the points I used were 90, 94, and I used 83 and 88. Okay, so I'll just use those 2 points to get my line of best fit. So first I'll get a slope, y2 minus y1, 90 minus 83. This is just 6/7. just take one of these 2 points, it doesn't matter which one. I'll take this one, and I'll plug in the values. So here's y, here's x. So 88 equals 6 over 7 times 83 plus b. Okay, and then I would solve for b here. Okay, so if I do that, let me grab my calculator here. 83 times 6. I'm left with 88 equals 498 over 7 plus b, sorry. And move this over to the other side. So common denominator minus 498 over 7 equals b. So I'll be left with 118 over 7 equals b. Okay, so the final equation of my line is just y equals 6 over 7x plus 118 over 7. Okay, so once I have the equation of a line of best fit, and I can then use this equation to decide or to solve for what numbers I might expect. Okay, we'll have an example of that in a bit. Okay? But again, the big point about a line of best fit, as long as it's running through the middle of the data, roughly in the same spot, everyone's will be a little bit different. Okay? But again, it's just an approximation, which means that everyone's will be different. Okay, so here's 2 examples. Okay, which of the following graphs best shows a strong negative association between D and T? Okay, so first we know the negative relationship goes in this direction, so I can cancel out C. Okay, and I can cancel out B. Okay, and then a strong negative. I'll draw 3 separate ones here. Okay, a strong negative just means all our points lie pretty well in a straight line. They're all close to that line. Okay, which in this example, our answer would be D. Okay, this would be strong. If I had a moderate, okay, that means it's okay. Some of them are pretty close, but then we have some that lie outside. They're just a little bit more spread out. And then finally we have a weak, which is very spread out. Okay, there's still somewhat of a shape that's taking place though. Okay, they're just obviously more spread out than the others. Okay, so interpreting this data set in this line of best fit. So Michael swam 2,000 yards on each of 18 days. So the scatter plot above shows his swim time, 4 and corresponding heart rate after each swim. Okay, the line of best fit for the data is also shown. For the swim that took 34 minutes, Michael's actual heart rate was about how many beats per minute less than the rate predicted by the line of best fit. Okay, so again, notice that they're using words like predicted. Okay, again, because the line of best fit is an approximation. Okay, it's not going to be perfect, but it'll give us a rough idea of what's going on. Okay, so our data set here, we have swimming time in minutes and heart rate measured in beats per minute. Okay, and this has a negative relationship because this just means as it's taking him longer, just means he's not swimming as hard, so he's not working as hard, so his heart rate is going down. Okay. So looking at the swim that took 34 minutes. Okay, that is that point right here. Okay, and his heart rate is at 148. Okay, and the line here is predicting, it's kind of difficult to see. Okay, but the line here is predicting that it would have been right here. Line predicts it would have took him 50 minutes. Okay, so to approximate the line of best fit, the swim that took 34, I go all the way up to the line, and then wherever I hit it, I go complete sideways. Okay, so it's predicting 150, when in actual fact it took him 148. Okay, so our answer here is just 2. 150 minus 148. Okay, this is called interpolating. Okay, it's interpolating because the value I'm looking for lies within my data set. Okay, extrapolating would mean I'm predicting for a number that's outside. And again, we'll have an example of that in a second. Okay, so a grocery store sells pints of raspberries and sets the price per pint each week. So the scatter plot above shows the price and the number of pints of raspberries sold for 19 weeks, along with the line of best fit and an equation for the line of best fit. Okay? So again, this is a strong negative correlation. Strong because all of these points are tightly packed to the line. Okay, so A here, according to the line of best fit, how many pints of raspberries would the grocery store be predicted to sell in a week when the price of raspberries is $4.50 per pint? Okay. So, using this line of best fit, okay, again, this is interpolating because $4.50 is within my data. Okay, I would go straight up to the line, and whenever I hit the line, I go straight across. Okay. Now, using the graph, because I'm drawing, is obviously not as accurate. Okay, so when they give me an equation, okay, and they're asking me for a question like this, I'll just take my equation, okay, and then I'll just plug in for which value they're giving me. So here they're giving me $4.50 per pint. Price per pint is my X value. So I'll plug in $4.50 right here. Okay, so when I do that, 32 times 450 is 144. So I'll have 233 minus 144, which just gives me 89. Okay, so pretty close to where my estimate was when I drew it. Okay, but this is just obviously a lot more accurate. Okay, so they could predict to sell 89 pints of raspberries if they set the price to $4.50. Okay, this is A. Okay, B. For how many of the 19 weeks shown was the number of pints of raspberries sold greater than the number predicted by line best fit? Okay, so this is a question where really all I have to do is count all of the dots that are greater than the line of best fit, so that are above the line of best fit. So if I do that, I got 1, 2, 3, 4, 5, 6, 7, 8. And so B would just be 8. Okay, now there are some that are close, like these two right here, this one and this one. Okay, but it's pretty obvious if it lies directly on the line, like this one perhaps. This is obviously right on the line. Okay, so just be careful of that when you're counting. Okay, but for B, really, all I have to do is count how many are above the line. Okay, if it asks for less than the number predicted, you would just count all of them below the line. Okay, so C, what is the best interpretation of the slope of the line of best fit in this context? Okay, so here's where we need to know what the units are and what they mean. So I know that slope is always y over x, right? Okay, which in this case would be number of pints divided by the price per pint. Okay, so if I interpret this, slope is just the change in y divided by the change in x, which means for every value I go up in the x, so for every 50-cent increase or for every $1 increase, I could expect to lose 32 number of pints sold. Okay, because my slope is negative 32, every time I go up $1, I'm going to lose 32 pints sold. Okay, that's all it means there. Okay, so what is the best interpretation of the y-intercept of the line of best fit here? Okay, so my y-intercept here is 233. And we should note that y-intercept happens when x equals 0. Well, if I look, what x equals 0 means here is the price per pint is 0. Okay? So if the price per pint were 0, they could expect to sell 233 pints of raspberries. Okay? In this case, doesn't necessarily make a whole lot of sense. Okay? Anytime your x value is price, okay, typically your y-intercept won't actually make sense like it does in this case. Okay, they would never sell something for $0. Okay, but our interpretation, that's what it would mean. Okay, so now we'll look at statistical analysis, okay, and what they'll mean for our data. So statistical analysis, we're just going to look at measures of central tendency, okay, and how we can represent the average or the middle of the data. So just an approximation. So mean, median, mode will give us this, okay, but one will be the most appropriate based on the data. Okay, so just a quick reminder of what they are. So mean is just the average. Okay, so if I have these numbers 1, 5, 4, 3, and 6, okay, the mean here would be the total. Sorry. The mean here would be the total divided by the number of items I have. Number of items. So in this case, 1 plus 5 is 6, plus 4 is 10, plus 3 is 13. My total is 19, and I have 5 items. Okay, so my average here is just 3.8, or my mean is 3.8. Okay, so the median is the term that lies directly in the middle of the data. So using these same numbers, when I'm doing the median, what I have to do is put them in order, okay, from least to biggest. So 1, 3, 4, 5, 6. Okay? And it's the term that lies directly in the middle. Okay, so there's 5 terms, so directly in the middle would be 4 in this case. Okay, it's both the third smallest and the third largest. Okay, so my median here would be 4. Okay, and then the mode, okay, is just the term that occurs the most often. Okay, so in this case, the only one that repeats more than once is 2. So my mode here is 2. Okay, mode is the one that we do not use very often. Okay, but it's still important to note what it is. Okay, outliers typically affect the mean, but not the median. Okay, so what an outlier is a number that is just so far away from all the other ones. Okay, so if we had like 1, 3, 4, and then 20. Okay, 20 is just so far removed from 1, 3, and 4 that we call it an outlier, and a lot of times we ignore it. Okay, outliers affect the mean. So if I were to do the mean of these terms, okay, we would have 24. We would have 28 divided by 4, which is 7. This would be my mean. Okay, my median, okay, 2 terms here, so I add them up, divided by 2. My median here is 3.5. Okay, if I look at the same set of data and eliminate the outlier, okay, well now my mean is 8 over 3, okay, which is 2.6. Okay, so by eliminating the outlier, okay, if we look at these two numbers, 7 and 2.6, okay, obviously made a huge difference there. Okay, if I'm looking at just 1, 3, and 4, now my median is 3. Okay, the difference between 3.5 and 3 is not much, okay, but it made a huge difference in my mean. Okay, so it's something to keep in mind. Okay, so here's a question. Here's a chart for the lengths of fish all in inches. Okay, so the table above lists the lengths to the nearest inch of a random sample of 21 brown bullhead fish. So the outlier measurement of 24 inches is an error. Okay. Of the mean, median, and range of the values listed, which will change the most if the 24-inch measurement is removed? Okay, so this is representing, or this is giving us a new measurement called range. Okay, where all range is the difference between the biggest number and the smallest number. So our range here is 24 minus 8. Our range is 16. Okay. So this asks, which will change the most? Okay, so our range here, if we eliminated this 24 now, and now our range is only going from 16 to 8. Okay, which is just 8. Okay, so we have how many? We have 1, 2, 3, 4, 5, 6, 7. We now have 20 fish in an 8-inch range. Okay, so pretty tightly packed data here. Okay, now by eliminating this outlier, okay, because there's so many terms, okay, because there's 20 terms, our mean will actually not change that much. Okay, our median here, okay, if we look at it, okay, we're looking at 21 fish. Okay, so our median here will be directly in the middle, so it'll be item number 11, okay, which is 12. Okay, even when I eliminate this outlier, okay, I still have 20 terms. My median will be between these two, which is still 12, so my median does not change at all. Okay, so I know that my range will change the most. Okay, if this, say they didn't put range, say they put mode, okay, my mode is still 12, no matter if I take out the 24 or not, okay, because 12 occurs 4 times no matter what. Okay, so in this case, if they changed range to mode, our mean would be affected the most, because median and range both did not change. Okay, so here's some mean and median questions here on the right. So the mean of m, n, and p is 8. If n plus n equals 15, then what is p? Okay, so my mean is 8. This is going to equal m plus n plus p divided by 3. Okay, so I know that 24 equals m plus n plus p. Okay, they tell me that m plus n is 15. Okay, so I know that this equals 15. So 24 equals 15 plus p. And just solve for p. P will just equal 9. Okay. Now, if you can interpret what that question means and just solve it in your head, by all means, go ahead. This is just a visual representation of what's happening. Okay, so I just joined a bowling league. We play 3 games a night. I scored 112 and 134 on my first 3 games. What do I have to bowl to get an average of 132 for the night? Okay, so again, I want my average, or my mean, to be 132. Okay, and this is going to equal game 1 plus game 2 plus game 3. Okay, divided by 3. So very, very similar to the previous question. Okay, so game 1 plus game 2 plus game 3 has to equal 396. I know game 1 was 112. I know game 2 was 134. And I'm trying to find what game 3 is. Okay, so 112 plus 134. 112 plus 134 is 246. 396 minus 246 is 150. So G3 would have to equal 150 for this to happen. Okay, so very similar to the previous question. Okay, so Kevin is both the 6th shortest and 6th tallest in his class. Okay, how many students are in the class? Okay, so I don't know how tall or any of them are, okay, but I don't really need to. All I need to know is that Kevin is the 6th shortest. Okay, so I'll just make a list. I'll say, here's 1, 2, 3, 4, 5, 6. Okay, this is Kevin. Okay, but he's also the 6th tallest. Okay, so the tallest is at the far end here, so I'll just count backwards. 1, 2, 3, 4, 5. Here's 6 again, which is Kevin. Okay, so how many students are in the class? So I just add up all these lines. I just end up with, there's 11 students in the class. Okay, so this is a median question. Okay, he lies directly in the middle. Okay, also note that 6 plus 6 is 12, and I just subtracted 1 from it. Okay, so if this was the 8th shortest and 8th tallest, okay, I can go 8 plus 8 minus 1. And so if there was 8 shortest, 8 tallest, okay, there would be 15 kids in the class. Okay, another way to interpret this would be that I know if he's the 6th shortest, that means there's 5 shorter than him and 5 taller than him. Okay, and then, so 5 plus Kevin himself. Okay, so there's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then we also get count for Kevin. Okay. So now interpreting tables and charts. Okay, so we looked at graphs. Now they may just give us a table or a chart of data, and we'll have to understand and analyze it by ourselves. Okay. So one thing to note what it is variation. Okay. So when looking at data, it is sometimes important to look at the variation or the spread in the data. And we need to know what standard deviation is, okay, but we will not have to calculate it. So standard deviation tells us, on average, how far off most people's scores were from the average. Okay, so if the standard deviation, okay, is low, and this means that most students' scores were close to the average. Okay, so there was not a big spread in the data. Okay, this would mean that everyone got about the same thing. They were all in the same region. Okay, by contrast, if the standard deviation is high, that means there's a huge change in the data. That means the data is very spread out. Okay, so based on the most recent data released on the SAT, the standard deviation is relatively high, meaning that SAT scores are all over the place. Okay, meaning some people do really well and some people also do very poorly. Okay, so if we were to look at this chart here, okay, here's our mean SAT score, okay, with a standard deviation of 194. Okay, so the way standard deviation works is that 68% of people fall within one standard deviation, okay, both plus and minus. Okay, so if I took 1083, to find the range, I would subtract 194, and I would also add 194. Okay, this would give us 889. This would give us 1277. Okay, which is this line and this line. So this area here, okay, this area here represents 68% of people that write the test. Okay. 95% of people fall within 2 standard deviations. Okay, so between 695 and 1471, again, all I did was just subtract another 194 and add another 194. So between here and here, that would account for 95% of people. Okay, and then obviously everything else out here would account for everyone else. But that's 3 standard deviations away, and that's only about 1% of people. So in a practical sense, and this is a question we may see, so the dot plots above show the distributions of scores on a current events quiz for 2 classes of 24 students. Okay, which of the following correctly compares the standard deviation of the scores in each of the classes? Okay. So, looking at this question, okay, if we look at this, the spread of this data, okay, is pretty tightly packed. Okay, if I was looking here, my average would be right here. Okay, and most people fall pretty tightly within that data. Okay, if I look at this question here, everyone's spread out. Right? There's the same amount of people got 0 as 5. Okay, so our standard deviation here is relatively high because there's such a big spread in the data. Okay, when we look at Class A, the spread's a lot tighter, so the variation is low, which means the standard deviation is smaller. Okay, so my correct answer here is A. Okay, so we just had to interpret what was given to us. And this next question, we again have to interpret what they're saying. So a quality control researcher at an electrics company is testing the life of the camera's batteries in a certain camera. So the researcher selects 100 batteries at random from the daily output of the batteries and finds that the life of the batteries has a mean of 342 with an associated margin of error of 18. So which of the following is the most appropriate conclusion based on the data? Okay, so my mean is 342. Okay, I have a margin of error of 18. Okay, which in this case I'll add 18 and I'll subtract 18 because it can go either way. Okay, so it gives me this 320, or sorry, this is 360 and 324 that all these answers are looking at. Okay, but now I have to interpret. So because this was just a sample of 100, okay, I can basically eliminate questions that say all. Okay, because whenever we're talking about data, okay, and we're given just a sample of 100, I can't conclude that all of them are true, or all of them fall within that data, because I haven't tested all of them. Okay, so I can eliminate A and B right off the jump. Okay, see if I read it. Okay, it is plausible that the mean life produced by the company that day is between 324 and 360. And if I look at D, it is plausible that the mean life of all the batteries ever produced by the company is between 324 and 360. Okay, again, I see words like all and ever. I can also eliminate D. Okay, so the key point here is that a lot of times when we're looking at data, and I'm just looking at a sample of the data, whenever they have extremes, like the word all or ever or none, okay, I can typically eliminate those answers. Just because from a sample of 100, I can't accurately say that all of them fall within that data. Okay, so we'll look at probability. Okay, probability is just the desired outcomes, or what we're looking for, divided by all the possible outcomes. Okay, so the probability of 2 or more events happening. Now, this will occur on the test. When we see the word or, when talking about probability, I will add the 2 probabilities together. So what is the probability of drawing either an ace or a queen from a deck of cards? Okay, so I'll look at the probability of drawing an ace. There's 4 aces in the deck, 52 cards. Okay, or drawing a queen, there's 4 queens. So my desired outcome, or what I'm looking for, there's 4 ways of that happening, compared to 52 total. Okay, so I can add these together. So there's an 8 in 52 chance of me pulling an ace or a queen. Okay, I could just reduce this to 2 over 13. Okay, if I wanted this probability as a percentage, just 2 divided by 13, it would be roughly 15%. So there's a 15% chance of me pulling an ace or a queen. Okay, so probability, they will a lot of times give us a chart and ask us to read the numbers from the chart. Okay, so here we have the stores deciding whether to install a new security system to prevent shoplifting. So based on store records, the security manager of the store estimates that 10,000 customers enter the store each week, 24 of whom will attempt to shoplift. So based on data provided from other users of the security system, the manager estimates the results of the new security system in detecting shoplifters would be shown in the table above. Okay, now again, that was a whole bunch of reading that I necessarily didn't have to do. Okay, so if I just take a quick look at the chart, okay, I can decipher what it's trying to tell me. Okay, and then if I just skip right to the question, according to the manager's estimates, if the alarm sounds for a customer, what is the probability that the customer did not attempt to shoplift? Okay, so if I were to just read this question, okay, I actually didn't really have to read all this. Okay, I can save myself about 45 seconds just by not reading that. Okay, now if the question might relate to that, then I want to go back and read it. Okay, but what I'm looking for in this question, okay, I want the probability that if the alarm sounds for a customer. Okay, so I'm only talking about this column now. Okay, what is the probability that the customer did not attempt to shoplift? So what I'm looking for is a customer that did not attempt to shoplift. Okay, so in this case I got 35. I'm going to divide by all the possible outcomes, so there's 56 total. So my total outcomes are 56. 35 divided by 56. And that reduces to 5 over 8, which is 62.5. Okay? So again, a lot of times when they give us this chart, okay, they might be, we will just deal with one column of the chart. And save ourselves some time by not necessarily having to read it. Okay, so here's a few more examples of looking at charts. Okay, so here we have results on the bar exam of law school graduates. Okay, and again, all the reading up to here, all of it up to here is just an explanation of what's going on in the chart. Okay, which just by looking at it, I pretty much know what's going on, right? So I don't really want to read that. All I will do is skip to the question. So what is the probability that the person chosen did not take the review course? Okay, so we're looking at people that passed the bar exam. Okay, that's right here. And I want to know the probability that the person chosen did not take the review course, which is here. So what I'm looking for is did not take divided by the total of people here, 7 over 25. Okay. So here's another chart here. Okay, I'll read this one. A group of 10 grade students responded to a survey that asked which math course they were currently enrolled in. The survey data were broken down as shown in the table above. So which of the following categories accounts for approximately 19% of all the of all the survey respondents? Okay, so now I'm going to compare to everyone. Okay, so 310 people. Okay, so there's two ways to do this question. Okay, it gives me the category, and I want to know which one is 19%. Okay, so what I can do is say A is orange. So females taking geometry is 53. Okay, females taking algebra 2 is 62. Okay, males taking geometry is 59. Okay, and males taking algebra 1 is 44. Okay, so two ways to do this. Okay, there's a long way and a short way. Okay, I'll do the long way first. Okay, and the long way would be to take all these numbers, 53, divide them by 310, and see what percentage that is. Okay, so if I did that, 53 divided by 310, that equals 0.17. Okay, which is not what I'm looking for here. Okay, that's only 17%. Okay, I could do that again for females taking algebra. Okay, and eventually one of these would equal 19% or 0.19. Okay, the faster way to do it is I'll just take 310, multiply it by 19%. Okay, it'll give me 58.9. Okay, 58.9, I'm looking at which of these numbers now is closest to 58.9. Okay, and when doing that, I know that males taking geometry is 59. Very, very close. I know that is approximately 19% of all the surveys, or of all the people that answered the survey. Okay, so either way you do this question, you'll end up with the right answer. But again, doing it that second way, it will just save you some time. Okay, so next example here, I have, based on the histogram above, which is closest to the average number of seeds per apple. Okay, so I'm looking for the mean here. Okay, I'm looking for number of seeds per apple. So I'm going to divide by the number of apples. Okay, so the number of seeds here. Okay, I'd have to do a little bit of work to find the number of seeds. Okay, there are 2 apples with 3 seeds. So there's 6 seeds total there. There's 4 apples with 5 seeds. So there's 20. Okay, there's 1 apple with 6 seeds. There's 2 apples with 7 seeds. And then there's 3 apples with 19 seeds. Okay, so that's the total number of seeds. I'm going to divide by the total number of apples. Okay, so the number of apples, I had 2 here. Those 4, I got 6 apples. There's another one, 7 apples. Okay, here's 2 apples here, so that's 9 apples, and then I have 12 apples total. Okay, so now I'll just do the math. 6 plus 20 plus 6 plus 14 plus 27 is 73. Divided by 12 is 6.08. Okay, so there's about 6 seeds per apple. Okay. So just remember that we're looking at totals, so the mean is the totals. Okay? So we have to count for the number of seeds, which is the area of this whole thing. Okay, not just 3. Okay, so again, here's a huge chart. Okay, it's the budgets for different programs in Kansas from 2007 to 2010. Okay, so if I skip straight to the questions, okay, which of the following best approximates the average rate in the annual budget for agriculture and natural resources in Kansas from 08 to 2010? Okay, rate of change, I know is slope. Okay, so I'm going to have to find the slope between this number and this number. Okay, again, we want to know approximately how much it is, so slope, I'll go 488,000 minus 358,000. Okay, divided by my x's. Okay, time is always going to be my x variable. So the time here, this is 2010 minus 2008. Okay, so when I do this math here real quick, it'll give me 130,000 divided by 2, which is 65,000. Okay, this is B. Okay, whenever I see the word rate or rate of change, I'm always going to look at slope. Okay, so I just wanted to know the slope of these two ordered pairs. Okay, so for 23, of the following, which program's ratio of its 07 budget to its 2010 budget is closest to HR, the HR's ratio between 07 and 2010? Okay, so looking at this real quick. Okay, first thing I want to know is I want to know HR's between 07 and 2010. Okay, which is about 4 million and about 6 million. Okay, and I'll throw that in a relationship. So we have about 4 million. And again, it's an approximation, so I just want to be relatively close. Okay, I can just reduce this to 2 over 3. Okay, so I'm looking for a ratio between this column and this column. It's as close to 2 over 3 as I can, or 2 to 3 as I can. Okay. Another way to do this, okay, is if I took this full number here, 4,051,050, and divided it by 5,921,379. Okay, that gives me 0.68. Okay. So again, the long way of doing this is to take all of this, all the numbers in this column and divide it by this. Okay, but again, that would take me a long time. Okay. Okay, but if I just use an approximation and that the ratio is 2 to 3, okay, now I can go through them real quick. Okay, this is 260,000. This is 460,000. That's not 2 to 3, so I can skip that one. Okay, this is about 1.5 to 1.7, which doesn't work. This is 14 to 14, doesn't work. Okay, this is 2 million, this is 3 million. Okay, that's pretty close to being 2 to 3. Okay, so I know rate then and there, education is my answer. Okay, if I want to verify my answer, if I take 2,164,607 and divide it by 3,008,036, okay, Sorry, I punched it in wrong. Okay, I get 0.71. Okay, which again is very close to 0.68, so I know I'm right. Okay, so again, showing you that there are many ways of doing questions. Some of them will just be more time consuming than others. Okay, so here, okay, are the sample questions to give a shot to. Okay, they're all in the calculator section. Okay, so something to note there. A lot of these questions would be very difficult without a calculator. Okay, so on the calculator part of the test, that is where the majority of these questions will lie. Okay, so give those a shot, and we are back to Tuesday night for our class. Okay, so see everyone Tuesday.